Hello again, everybody. I am going to be doing this one today. And good news for you guys, this is the last video until Monday when I'm absent again. Ha, ha, ha. This is the last video. I'll be back on Monday for page for that you'll have to watch for a while, which is good news for you. Now, on Monday, you'll see that we have review stations. We'll just make sure that you know what you're supposed to know. And again, I really don't expect to hear any excuses. If you didn't do what you were supposed to, that means you have homework and you need to figure it out because you are smart enough and you are capable to be able to figure out how to do the work that was assigned for you. We're going to have a quiz on Tuesday. It is not going to be online. I actually sounded fine this morning. And then I sounded a little bit worse. But now I just made a really gross sound, and I think I sound better. Okay. It is not online. It will be a paper test in class quiz. In class, it will be worth 50 points. Technically 40 points, but we'll make it out 50. Other thing that you should probably know about this driving project. So this driving project is going to be assigned on today. I'm not here today, though. I think for my third period class, you guys got it yesterday. I'm going to talk about that on Monday, but you're welcome to work ahead. And if you want to get it out of the way, you're welcome to do it over this weekend. And if you have any questions, you're welcome to email me about it. Okay. As far as collecting homework goes and checking homework and all that, I don't know, guys. That might actually be something that I'll do on the quiz day on Tuesday and on Monday, maybe. Although Monday, I really want to help you. But let's get going with the video and what we need to do here. Let's go to page 20 through 24. Is this 20 through 24? So we're going to work on Riemann sums and integral notation today. We're also going to work on some properties of integral. Wait, pause. I was freaking out for a second because when we made these new packets, I thought she had already done this, but this is just review I think she's doing. She being Miss Schwartz. So what I'm going to have you do actually is pause the video and try 1 and 2 on your own. This is just review of what you guys did the last time as a little warm-up. It says, use the limit definition of an integral to calculate the following definite integrals. Draw a sketch to help you understand what you are calculating. So she gave you the limit definition right here. Please pause the video. Try it on your own. Thank you. Pause the video. Okay, let's see if this is what you got. Screen for you. Uh-oh. Okay. A was 2, B was 6. Hopefully you were able to get that part. Those are your limits of integration. Your width is 6 minus 2 over n. B minus a over n, which is 4 over n. Your height is all here in red. If you didn't get that, copy that down. That's more algebra, though, that you're just plugging 2 plus 4 over ni in for x, squaring it, adding the 5, and that's what that f of a plus b minus a over ni is. Okay, and then I plugged everything into that formula. It started in green. Limit as n goes to infinity. That's what the integral is equal to. For all these rectangles that we're adding up is going to be here. That's the red part. Let me put this part in green because that's what I had really intended. And then after that, it's all algebra. I mean, the calculus part is done. So what I did a couple things in one step. Notice the summation disappeared here because I applied the formulas to the I squared, and the constant. And I did 9 times 4 is 36n over n. 16 times 4 is 64 over n squared times n plus 1 over 2 plus 64 over n cubed times, again, that formula for I squared. So that's how I got those numbers. I just distributed the 4 over n into everything. And then every year I have students that want to multiply this out and multiply this part out. And I can't tell you that is just, it's good that you're practicing that. Frankly, it's a waste of your time. And you know I'm big on time when it comes to timed test and you being efficient. So what I'm going to recommend is you make sure you understand the strategy that I'm showing you here. This first term was pretty easy. N over n, those cancel, you just get 36. For this term, what I do is I take the lead term of each factor and I multiply them together. I take 64, I take the n, and I take an n from this factor. I don't care about the plus 1 because when I am talking about infinity, the plus 1 is kind of irrelevant. So I leave the plus 1 out. Now, the bottom was pretty easy. I just got 2n squared, and when I reduced it, that was pretty easy to get 32. Hopefully you're able to see that that was that easy, and if not, you got to ask questions. Okay, for the next part, for the next term. So again, I look at the lead term of each factor. A factor is something that is being multiplied. A lead term is the biggest value in that, the biggest exponent. So 64 here is the lead term of that factor because there is no other exponent. Here there is a lead term of n. In this factor, there's a lead term of n again. In the last factor, there's a lead term of 2n. So I can do 64 times n times 2n over n cubed, 6n cubed. The n cubes cancel, which is what I usually like to see. And the 2 and the 6 can reduce to 3, so I got 64 thirds. And after that, it was just some arithmetic to get me 268 over 3 as the answer. I checked it on Desmos. On Desmos, the answer is 89.3 repeating. I would expect on an AP test that this would be the question, the answer that they would give you. And honestly, I think we'll give you a calculator on your quiz, but this is a no calculator question. And my tip for you is stands as before. If you're struggling with the arithmetic, do not use the calculator as a crutch. Okay, let me show you that graph quickly because the question asks you to draw a picture and help you understand what you're calculating. What that 89.33 represents is going to be the area bounded by x equals 2, by x equals 6, and the x-axis, and the curve. All this shaded area, is 89 1/3 units. That's what our calculus tells us. Okay, let's do the next one. Please pause the video. Try the next one on your own. Oh, ask questions to your group. Oh, like really ask questions to your group. Like really try to work at this so we can move on to the lesson. Okay, here's all the work. Please pause the video at any point to make sure that you see all the work. But because we have a lot to go on, and I already used 8 minutes of the video to go over these first two problems, I want to move on. The answer here should have been 69. Pause the video at any point to just look at the work and see what kind of steps that I took that maybe you didn't take because your answer resulted in the wrong answer. If you got it, move on. Here's what the graph looks like, just in case you want to see. And that area is exactly 69 square units. Let's go on to the big show for today. So we're working on properties of integrals. Now that we see where integrals come from and we see where the symbol comes from, we can actually go with the, we can use some properties and kind of use them like we did derivatives before. Without further ado, kids like these because they're pretty intuitive. In fact, every year, and I wish I was in class to do this, I know you do too, in class every year I always have kids that can kind of come up with these on their own. We have the first one, which is straightforward. It means you can add and subtract, but you cannot distribute to multiplication and division. I don't know anything that causes more fury in my blood if I see distribution to multiplication and division. Cannot distribute to multiplication and division. Only to addition and subtraction. And what can you not distribute? You cannot distribute integrals to multiplication and division. Okay, for the constant multiple rule, I like that one. That means I can just take a number, a singular number that does not have an x. A number with no x. You can take that out of the integral, and there you go. Okay, reverse integral. There's a little note at the top of the page that said a is less than b. So what we do here is if, hold on just a second here, I want to see, yeah. If it was, I think what Ms. Schwartz had intended to write is that if you had this integral, like from b to a of g of x dx, well, basically on a graph, here's a and here is b, and we always go from left to right. Well, to go, if you're going from b to a, you're going in a negative direction. So what we can do is take out a negative and switch the limits of integration. Okay, zero length integral. The integral from a to a. Well, from a to a, here's a, and now I go to a. Oh, I can't go anywhere. Zero. Adding intervals. Okay, this is actually a geometry idea. Segment addition. If you're going from a to b, and then b to c, it's similar to the idea of just going from a to c. That's right. So we can actually combine integrals if we need to. Okay. And by the way, these are, I'm going to use the word biconditional. It works both ways. So not only all of these, well, I'm thinking. They all kind of work both ways. But this is the big one that I need you to know can work in two different directions. So sometimes you'll get an integral that actually needs to be broken up into two different integrals. And sometimes you'll get two integrals that could be just written as one. That makes it simpler. So again, the adding intervals is a really important one. I'm actually going to highlight that one. That one's an important one. You need to know that one. Again, that property works both ways. Absolute value of a function. Okay. The absolute value of a function, here's what we do here. So if we have the integral of f of x dx from 0 to 8, so this will illustrate that adding property. Well, then that means that we have to take the integral from 0 to 8 of f of x dx. I'm sorry, that's not true. We have to take the integral from 0 to 5 of f of x, and then plus a negative value of 5 to 8 of f of x. And again, I should have put my dx on both integrals. The reason I need this minus here is because this value here is a negative value. How do I know that? Well, I know that this value is negative because it's beneath the x-axis. So when I do the integral on that, that's going to lead me to a negative area. But if I want the absolute value, I want this to be a positive. So I want this area to be up here. So the way I do that is I subtract it. I subtract the negative. When I subtract the negative, I add up positive areas, which means I get positive values. That's going to come up as a question later on about area, signs of area. And all I'm going to tell you right now is you're just going to have to pay attention to the context. If it tells you area, your value should be positive. If it just asks for the value of an integral, that area could be negative. But again, when we go into position, velocity, and acceleration, I mean, then the rules need to be explained a bit more. Okay. What I'm going to do first is I'm going to look at my units. Okay, I'm going ones by ones. Good. Next, I'm just going to write in a little bit for each one. 0.5, 1, 1, 1, 1, 1, 0.5. This is going to help me big time. 0.5, negative 0.5, negative 1, negative 0.5, -1, -1. Oh, man. What is this? This is 1. That's going to be down 2 over 1. So let's see. That's going to be an area of 1 total. So that's -1. The reason I did this is so that way when I get these kind of problems where I just have to find an integral based on a graph, I really just have to find the area bounded between the curve and the x-axis, the function and the x-axis. So let's go. -3 to -3. I love these. These are quick. That's 0 because you're not going anywhere. From -3 to -1, let's see what we got here. -3 to -1, I'm just going to add up those areas, and it looks like I get 4. I got 4 from 1, 2, 3, 4. All of that area. From -1 to -3. Well, -1 to -3, oh, hey, -1 is bigger than -3. That's not right. Let's go ahead and switch this to -3, -1 of f of x dx and feel the power that you are bequeathing. And then you can go ahead and just do what you just did. So this value was 4. So now you need a -4. And you don't really have to write this integral, but I do want you to practice writing it for the first few times because you've never done that before. And then after a while, you can skip that part because if you're going from -1 to -3, you're clearly you're taking positive area, right? All of this area was positive area, but you're going in a negative direction, which makes the area then negative. Okay. Let's go to 4. Okay, from 1 to 4. From 1 to 4, I'm just going to add up all my little boxes here. I got 1, 2, 3, 4. I got -4. And if I made a mistake, you're going to tell me on Monday. From 4 to 1, all right, because I'm short on time, I'm going to go ahead and just tell you that that's the opposite of 4. The opposite of this 4. Opposite of -4 is 4. For 6, from -5 to 1. So from -5 to 1, well, let's see what this. So I could add all these little areas of the boxes. I could also just find the area of the trapezoid. I mean, there's a lot of ways to do this from -5 to 1. Whatever suits your fancy. I don't want to add all those numbers, so I'll just find the area quickly. The base is 6. This base is 2, because we will need trapezoids later. The height is 2. And the area of a trapezoid is 1/2 base times 1 plus base 2, and then times height. Okay, so we got 8 over 4 times 2, which is 4. Well, that can't be right. Let's try that again. Oh, I see what I did wrong. I see it. This should be a 2. Let's see if that worked. Base 1 plus base 2 divided by 2 should be quicker to just do the boxes. Okay, so that should be 8. Okay. And I'm going to assume I checked on the boxes. 1, 2, 3, 4, 5, 6, 7, 8. Good. Number 7, -5 to 5. So here's one that I can use that adding property on, even though it doesn't tell me to. I can just use it because I can feel like it. I could break this into -5 to 1, since that's the problem I previously solved, plus the integral from 1 to 5. And that's a problem that I haven't solved. I know this value is 8, so now I just need to get this other value, which based on the graph looks like 1, 2, 3, 4, 5, 6. So it's going to be 8 plus -6, which is 2. Number 8. Okay, now I got to take all of this area and make this negative. So the way I deal with absolute values in an integrand, okay, and the integrand means inside the integral, is I can just do the same exact thing that I did in 7 mostly. So equals the integral from -5 to 1 of f of x, because this is all positive area, and then subtract the negative area. And if I do 8 minus negative 6, this looks like 26. If I do 8 minus negative 6, I get 14. Okay, from negative 5 to 1 of f of x. So again, this is another one of these that I need to do the adding property. And I'm running out of room here, so I'm just going to bring this down here. Okay, so for number 9, negative 5 to 1 of f of x dx, please put your dx's, plus the integral from negative 5 to 1 of 2 dx. Okay, well, the negative 5 to 1, I believe we got, I have no idea, 8. We got 8. Okay, 8 plus this one. Take a look at the graph of y equals 2, because that's not on there. The graph of y equals 2 looks like this. From negative 5 to 1 makes a nice rectangle, which has a total of 6 for the base, 2 for the height, which means that we get a total of 12. And again, we got that from 6 times 2. And that gives me an area of 20 for number 9. For number 10. 3 times, well, let's see. I can take the 3 out because that doesn't have an x with it. So negative 5, 1, f of x dx. By the way, this one, that idea of taking a value out, it makes integrals so much easier sometimes. So again, something that you really want to just know. So now we have 3 times 8 because the same value is 8. That's 24. And this last one, oh boy. Oh boy. All right, so let's just break this. Oh, geez, we're going to need a lot of room. This is going to be a long problem. Let's just draw some bars here. Okay, we're going to do the first part. Integral from negative 5 to 5 of 3 dx. I'm going to not tell you. I'm going to see if you can get it on your own now. For similar reasons here, I'm going to tell you that this is going to be 30. And I believe the other part, the negative 5 to 5 of the absolute value of f of x dx, I believe we already said that that one was going to be, we did that one, didn't we? Yeah, that's number 8. We found that to be 14. So when you add them up, you get 44. That wasn't that bad. All right, we have 2 more pages to go. And I'm not stopping. Okay, so this is kind of what we just did before. If you have a value of 3, this is now using geometry because we can use geometry to find values of area. I mean, that kind of makes sense. Okay, so we got from negative 3 to 5 of the height of 3. That's y equals 3. That's this 3 right there. And again, your height is 3. Your base is 8. So altogether, you're getting 24 for the area of this rectangle. From 1 to 4. So here's 1, here's 4. And x looks like this. Okay, this is going to be a trapezoid. It's a trapezoid standing up, so it looks kind of like this. Your height is 1 here. Your height here is 4. Think about that before you ask somebody why. Your base, this value here is 3. And remember, we take the average of the 2 bases. Remember, these are perpendicular. We take the average of the 2 bases and multiply it times the height. So the average of the 2 bases is going to be 2.5. We have 4 plus 1 over 2. And then we're multiplying it times the quote-unquote height, which is going to be 15 over 2. 2 minus x. All right. I'm going to rewrite that because I don't really want to draw. Well, I'll draw it. Here's 2. Minus x looks like this. Okay, at negative 2. I got to plug in points here and make this graph right. Okay, so this is going to be at 4. This is at negative 2. And then 2 minus 4 is at negative 2. So that's a negative 2. Okay, so here I have two triangles. I have a green one, which has positive area. I have a red one, which has negative area. You pause the video now. And now I'll just tell you. This area, and again, your x-intercept is 2. Okay, so we got a base of 4. We have a height of 4 for this triangle. So your green area is going to be base times height, which is 8, divided by 2, of course. Your red area has a base of 2, has a height of negative 2. So we have a negative 4 over 2, which is a negative 2. So your value should be 6. Okay, x minus 3 from 0 to 6. Remember, the graph of x minus 3 just shifts the graph 2 units to the right. I'm sorry, 3 units to the right. 6, 3, and 0. So you're finding the area of these two triangles. They're symmetric. So one other way that we could do this, it's not an easier way, is going to be 2 times the integral from 0 to 3 of the absolute value of x dx. I would stop the video and make sure you understand that one, because that one was kind of a tricky one. I pulled a trick out of my hat to do that one. I just changed the entire problem to something way easier, which I did 2 times the integral from 0 to 3 of the absolute value of x, not x minus 3, dx, because I saw that these were symmetric. And the value of one of those areas was, let's see, 3 times the height of 3 is 9, so 9 over 2. All right, so I got 2 times 9 over 2, which is 9. I told you the time would come when you would have to wonder when what shape these make. If I was in class, I'd be very impressed that you remembered. This makes a semicircle. I got to get going. I got to go to the hospital for my wife again, so I'm rushing along here. Okay, but you have the ability to pause and ask questions, etc. So don't you start making excuses. Okay, your radius is 4. You're finding the area of the semicircle. Remember, this makes the area of a semicircle. Let's find the area of it. The area of the semicircle is 16 pi over 2, which is 8 pi. Okay, well, that's our answer, 8 pi. And then for the last one, well, this one we have to use, put an end parenthesis there. We have to use 2 rules. We have to use 0 to 3 of 3 dx, and then subtract the 0 to 3 of the square root of 9 minus x squared dx. Come on. And let's see what we get here. This first one is going to be, and maybe some people already saw it, that's going to be 9 minus. If you're not sure for the blue, draw a graph. For the second one, we have a semicircle, but this time only from 0 to 3 with a radius of 3. So here's it is. So now we only have a quarter of a circle with r equals 3. So let's see, we have 9 pi over 4. So r was 3. This was 3 squared, which is 9 pi over 4. And that's the fine answer. That's your answer. All right, for the final part, evaluating using a table. I'm just going to set these up for you. I am not going to actually solve these for you because I got to get going here. So a left Riemann sum. Watch the pattern. To do a left Riemann sum, notice my intervals are not uniform. Intervals not uniform. And actually, I just decided I'm going to do this one in class for you because I got to get going. Have a good day, guys.